So during that first lab, you worked on installing Datomic Cloud, connecting through the Bastion, and verifying that you could do a minimal bit of operation against Datomic. And if you didn't notice this, or if you were not in the Slack, I dropped the slides for today as a PDF into the Slack room. So if you want to follow along in the slides, you can grab them out of the Slack room on your laptop or mobile device and follow along on the slides. If we make additions to the slides based on cool things you bring up, then I will drop another copy of slides at the end of the day, so you get the stuff that we changed during the day. So I want to talk now about the information model in Datomic, and this is going to divide roughly into 5 things. One, just talking about notation. So this will be of particular interest for people who are not familiar with Clojure as much. For Clojure folks, it'll be a review. Then we're going to talk about datoms. Datoms are the primary foundation on which a Datomic database is built, and a datum is a 5-tuple that's inspired by triple stores, but influenced by the notation or by the notion of immutability. A database is nothing more than a set of datoms. So all of the data in your system is a potentially enormous set of these 5-tuple datoms. And then we're going to talk about entities, which are things in the world. So a person, or an item in inventory, or a medical experiment, and how we get from datoms to a description in aggregate of some entity about which we know 5 things, or 10 things, or 1,000 things. And then finally, we'll talk about schema and how to model in Datomic and how to create and install schema. So let's start with notation. The notation used in Datomic is what's called the extensible data notation, or Eden. And this is Clojure, right? The Eden data notation was extracted. It's a subset of the actual Clojure language. If you squint at it a little bit, it looks like JSON, but with a few differences, and those differences are critical to our ability to use it to make a database. Has anyone ever programmed in JSON? We actually have to write your program in JSON. One place where you have to do that is if you're writing an AWS CloudFormation template in JSON. That is such a terrible experience that even YAML is better. So people are now switching to programming. But YAML and Eden, or YAML and JSON, are really insufficient for writing programs for a couple of reasons, as we'll see. So the base types in Eden include strings, which are inside double quote, like the string foo, characters, which are preceded by backslash, so here the backslash f, the letter F. There are integers, both in platform limited, so just a number, and in arbitrary sizes. So the capital N means the equivalent of a Java big integer. There are floating point numbers, again, platform limited. 3.14 is a Java double, and 3.14m is a Java big decimal. There are Booleans. I thought about listing all of them, but I only listed one. You'll have to guess what the other one is. There is a value that represents nothing, which is nil. And then, and this is incredibly important, there are not one, but 2 different types that represent names of things. There's symbols, which are unadorned names, and then there are keywords, which are adorned with a colon. And this is a fairly distinguishing characteristic of Clojure, which is having not one, but 2 different name types. There are a lot of languages that you program in that don't have a symbolic type at all. Java, for example. And then there are languages that, like Ruby, that have a single symbolic type, but it's unusual to have 2 symbolic types. And it's particularly enabling when you want to do something like write a query language or a transaction language as a data DSL that's just inside your language. There are 4 types for aggregates. There are lists, which are inside rounded parens. This represents something that you can access hand over hand sequentially. There are indexed ordered collections, which are vectors. So these support both sequential and random access, and they're inside the square brackets. There are associative collections that associate the key with a value, maps. They have curly braces. And it's very common for maps to use keywords. You don't have to, right? Everything composes, everything nests. But it's very common to use keywords because we use maps in Clojure to represent entities in the real world. And entities have named attributes. And we have a naming type in Clojure, which is a keyword. So it's very common, but not required, that the keys in a map be keywords. So here we have the key A and the key B. I'll mention here also that commas are white space in Clojure. So if you need to have a training wheels period where you put commas between everything, you're more than welcome to do that. Clojure won't care. But my guess is once you realize that you don't need them to read things, you'll eventually stop using them. And then you'll start making syntax errors when you use other languages. Sets look almost like maps structurally. They use the curly brace and the pound prefix. Pro tip for reading Clojure, anytime you read the pound character, that means special interpretation of the next character is about to happen. So the Clojure parser is designed so that it only has to do that in one place. That's the only character that works that way. And so anytime you see a pound, your antenna should go up and go, special thing is about to happen here. In this case, the thing that's special that's happening is fairly small. It's just that this is a set instead of a map. So compared to, say, JSON, we need all of these things in order just to talk about information. Right? Without a type that represents names, you can't talk about variables, you can't talk about attributes of things, and so forth, without having confusion with strings. But you're also going to run into other things that are data in your program that are not covered in this basic list. So the other thing that Eden includes is an extensibility mechanism. You can have pound followed by a name, followed by some Eden, and that now says, well, we're going to interpret that form in the context of that name. There's a very important idea inside of this, which is what happens when you see one of these special names and you don't know how to interpret it. I make up a name in my program. I create something and I call it Roscoe. Pound Roscoe, followed by some data. And now your program is trying to read data that I sent you. Everything must be recursively understandable as Eden at the bottom. So you can go, ooh, Roscoe, I don't know what that is, but you can put a piece of data in a bag labeled Roscoe and say, okay, I don't know what this is, but whoever cared about it was thinking of Roscoe. And then you can flow that on to some consumer later by keeping track of the things that you didn't know. This is incredibly important because people get this wrong all the time. And when you get this wrong, you break all the intermediaries in your system. Right? You make a change over here that needs to flow over here, and there's 12 intermediaries in between, and every single one of them breaks because it doesn't know what Roscoe is. With this system, you don't have to know what Roscoe is. All you have to do is say, okay, I don't know what that is, but I'm going to flow it along. For our use, there are a couple of built-in custom data types that you'll run into while doing Datomic work. One of them is an instant, which is an RFC 3339 date as a string, and it's pound inst prefix. And the other one is a UUID, pound UUID followed by a string. So that's notation, and that's all you ever need to learn. It's a pretty small set. Now let's talk about information. A datum is a granular atomic fact. Granular means small. I would almost dare say minimal. Right? If you said anything smaller than a datum, you wouldn't have a fact. It's immutable. So you make datums, and a datomic system evolves over time by accreting new datums. Datums never go away, ever. Asterisk. And a datum is a 5-tuple. It's an entity, an attribute, a value, a transaction, and an operation. The entity is some identifier that represents the real-world entity we care about. The attribute is a name that says there's this named attribute of that entity we care about. The value is the value for that attribute. The transaction is a reference to the transaction that added this piece of information to the system. So later we'll say the phrase reified transactions. That means transactions are actually objects in the system, and you could talk about them. Here's a test for understanding. Right? Git has reified transactions. What are they called? Commits. Right? If you're not sure what I mean when I say reified transaction, and a git commit can have data about it. Not a lot, really, but what kind of data can a git commit have? It can reference other commits. It can have a commit message. It can be tagged. Right? There's various pieces of information that you can have about a git commit. And they allow you to talk about the git commit. They allow you to talk about its purpose, where it came from, where it's going, and so forth. With Datomic, because transactions are entities, you can talk about them. That talking, though, is open-ended. They can have arbitrary attributes as well, and we'll see that more later. And then operations says, are we adding this fact to the system or removing this fact from the system? So the operation is true if we're adding it to the system and false if we're not. So here are some example datums. Jane likes broccoli as of time 1008. And I'll say time, or I'll just say the letter T. So at T 1008, Jane likes broccoli. True. We put that in the system. At T 1008, Jane also likes pizza. So there's nothing about the system that says Jane can't like more than one thing. Good for Jane. And then at some point, Jane sort of loses the feels for pizza. So at time 1148, Jane no longer likes pizza. And so here you start to get the idea for what deletion looks like in the datomic world. There is no deletion, right? There is Jane used to like pizza, and now Jane doesn't like pizza anymore. Now, in fact, we don't actually store Jane as a name. It's stored as an opaque identifier inside the system called an entity ID. And we don't store the names of all the attributes, right? We store those in one place. So the attribute is also an opaque identifier. So if you were to look at the actual raw datums, you wouldn't see Jane in E position. You would see some famous number or some not very famous number in E position. You wouldn't see likes. You would see some not very famous number, like 63. Now, that's your whole database. Everything in your database is stored this way. So this is called a universal relation. By contrast, when you model with SQL, you're using specific relations. And you have to describe them in advance. So the first thing you do before you put things into SQL is you make a what? A table. You have to make a table. That's a specific relation. And as soon as you make a table, you're making slots. And you have all those problems that I talked about before, which are that as soon as you make slots, you have some information that doesn't match your slots, but it still is about that entity. Right? And we have a very open world belief in Datomic in that sense, right? We believe that you could find out new information later about an entity. So the database stores things efficiently, and you've seen a little bit of a hint of that. We store numeric IDs. I would contrast that with a system that was, say, a naive RDF implementation, where you have triple store, which has a lot of these characteristics in common, but they're not worried about being super concise. And in fact, they're making the open world assumption in a much bigger way. They're saying we have to have a globally unique name for every entity in the system before we can sort of move along. Database is sorted in multiple ways, and we'll see those sort orders in a minute. And this is an underpinning of the ability to perform logic on the database. Right? If you don't have sorts, if you don't have the data sorted in different ways, you can't find things. And it's accumulate only. What does this mean for your use? Every time people talk about NoSQL, they like to put them in categories based on the structure they impose. So relational databases impose rows, right? If all your problems look like rows, you use a relational database. Sometimes for analytics databases, people will use a column store. So that imposes columns, right? The primary way that you get to things is via columns. There are key value stores. So key value stores say our basic unit of information is not even enough to be a complete fact. I can say things like likes pizza, right? You can say that with a key value store, likes pizza. What are you missing? Who likes the pizza, right? So with something like a key value store, you don't really have enough at that level to have information. You can have document stores. Obviously, you can have arbitrary stuff in a document that's nested. And you can have graph stores where you have this relationship connects along an edge to that relationship, connects along an edge to that relationship. That's become very popular because of social graphs now. This style of having a universal relation lets you model all these other styles more or less directly, and is particularly well suited to the query language, Datalog, and to pull, which we'll see later. So Datomic sorts everything, and these indexes are named by how you sort. So AVET says we sort by attribute. All the likes are together, followed by pizza. All the likes pizzas are together, followed by who does the liking. All the Janes are together, followed by time. So when I say AVAT, you imagine that all the facts about a particular thing. What kind of store is this useful for? Well, this is very similar to a key value store because keys are like A's, and values are like V's. So the things you might do with a key value store, Datomic can do by following the AVAT index. And let me just jump to the end. I'm showing you sort of under the covers right now. How often when you're programming in Datomic are you going to say, call the AVAT index? Never, right? You don't call the AVAT index. You issue a data log query, and Datomic says, aha, I can answer that query efficiently by using the AVAT index, and it selects the index. Row-oriented means all the stuff about Jane is in a different place from all the stuff about Joe, from all the stuff about Jeff. And so it's entity leading, so EAVT. So this is suitable for things that are like a traditional SQL database where you go by row. Tell me everything about Keith. Right? I want to know everything about a single person or everything about a single entity in the system. The AEVT attribute is suitable for the kinds of things that people do with column stores. I don't want all of the attributes about a particular entity. I just want all the attributes. I'm going to fly through all of those. Document is a little bit more subtle. So Datomic will let you use the entity leading index to find an entity, but then Datomic has a notion when you're declaring schema attributes of calling something a component. When you say something is a component of something else, that is among other things, it is a storage hint to Datomic about where to put that stuff. So it's close. So I can say, the classic example I like to use is order line items, right? A line item is part of an order. It's a component of an order. A line item does not exist outside of an order. So a line item is declared as a component of an order. You can get all of those things in one go. And then graph stores are about the values. The value index lets you work backwards to who has a value. So I can say, I can use facts about me to say who are my friends. I can navigate that way, starting from E. But navigating the other way, if I have someone and I say, is that person a friend of Stu, then I want to come in the other direction. Right? So I want to start with the value. So the VAET index lets you do that. So for a wide variety of uses, the Datomic database is built around the notion that a row or column or document or a graph store is a premature optimization. Right? You are privileging a certain kind of access and making other kinds of access really difficult. Whereas with a more granular approach with datoms, you're saying, you know what? We want to make all of these pretty good. And so you can have a store that supports all of these things. And in real-world terms, what this often means is that people are using Datomic don't end up having to pour their database data from one data to another to support different kinds of queries. Datomic is time-aware all the time. So when you get a database value back from a connection, as you did a little bit in the previous lab and we'll be doing more in the next lab, that is the current state of the world. If you ask for an as-of database, you can say, what did things look like at a point in the past? And then issue your query against that. A since database is probably the most unusual one. It says, give me only the things that have changed since some point in the past. So this is a database with old stuff shaved off and only the new. A transaction report tells me what did the database look like before a change, what did the database look like after a change, and what was the change. And this is actually what Datomic returns from a transaction. And this is a critical thing to understand. When you issue a transaction in Datomic, you get back the value of the database before a transaction, the value of the database after the transaction, and what data got added. And it's always added, right? There's never data being subtracted. So what data has been accreted into the system. What do you get back from a transaction in most traditional databases? Ta-da, we got it. Maybe a little bit of information, right? Do you know what the database looked like before the transaction? Can you get to what the database looked like before the transaction? No, it's gone. Can you get to what the database looked like after the transaction? Not necessarily, because by the time you go back, what could have happened? If you really want, in a mutable database, if you really want to say, I want to hold on to this value of the database at a point in time, what would you have to do? You'd have to copy the entire database. So that's what we're getting away from with this kind of approach. You can also do what's called a with database. With allows you to speculatively add datums in memory without actually adding datums to the database. So this allows you to issue kind of what-if queries. Right? What if this data were in the database what would our profits be next quarter? Or how many things, how many trucks would have to go from here to there if this happened? So with gives you an ability to do that. And then the history view of the database says, you know what? Shields are down. We're going to show you everything that was true ever. So you will see what was true in the past and what was true now. And this is useful when you want to do audit trail type things. I want to know everything that is true now about this piece of data where something went wrong, but I also want to know what was true about it in the past, because when something went wrong, that was in the past. So I want to know what things looked like back then. On top of these on datums, there's this notion in the real world of entities. Do we ever model everything about a real world entity? This is an easy one. Do we? Of course not. The word modeling means we're selecting some things to care about and some things not to care about. With a traditional database, when do we decide what we're going to care about? When we make tables. Right? With a relational database, we decide what we're going to care about when we make tables. With Datomic, we decide what we're going to care about when we care about it. Right? If we care about something, about an entity, we add it. Now, let me just be fair to tables for a second, because I was sort of hoping that one of you would jump up and make the impassioned plea for tables and slots. Tables do give you the ability to do some things. Right? You can easily make a rule with tables that say, this row must be completely filled, or I will not consider this valid. You can do you can impose structural rules. All right, we're not into that. So but that's a benefit. That's a benefit that we disavow in light of what we would like to see as other benefits instead. But you can, with tables, you can say, you know what? You're not a real order until you have these 17 properties. And you can get structural validation. Now, with Datomic, of course, you can still do validation of that sort. You can do functional validation. You could say, I'm going to use a function to look at a particular order and see if it has those 17 values. And if it does, I'm going to say, yay, and if not, no. So there are other ways to do that. But that is the thing that's being traded off here. But you're getting something enormous here. How much time have you spent dealing with the brittleness of your database? Dealing with joining to a table to get more information about the same entity because you didn't have that information in the first table. And of course, that kind of complexity sort of caroms through your system. Because if on the database side, I have a table joined to another table, joined to another table, what does that look like on the programming side? A lot of programmers, the first thing they're going to do is say, oh, let's turn that into objects. Oh man, that's really not fun. Let's make a library to turn that into objects that automates dealing with the impedance mismatch between those things. And then you find yourself spending your life working with ORMs instead of actually working with your data. We hate ORMs. So, that being said, we have entities in the world, and we only have datums in Datomic. So we have this very granular thing. How do we get from datums to entities? Well, it's really straightforward. Let's imagine that we have a map that represents some entity. Here we're talking about Jane. Jane likes broccoli. Jane likes pizza. That can be mechanically translated into datums, right? You can walk up to a table and say, let me find all the things that are 1001. Let me look up the names of all their attributes. Let me look up all their values. If the values are themselves entities, apply that recursively. Drill back in one level and say, let me dig up the rest of the stuff. The important thing about this transformation is there's only one way you could make it. That's what I mean when I say that there's no impedance mismatch. Once I tell you we're going to play a game where we turn datums into nested maps, there's only one way to play that game, which is you start with a datum, all the attributes become keys, all the values become values. If those values themselves are entities, you play the game again, and you keep going, and you keep going, and you keep going. So where's schema in all this? I haven't said anything about schema, and it's going to turn out to be the case in just a moment that you cannot just walk up to Datomic and put arbitrary data in without saying a little bit about schema. So first, let me try to revitalize schema a little bit. Right? Schema is a good thing. Schema is making statements about your data that give you power over your data. And so whenever anybody says something is schemaless, I always hear powerless, right? That they don't have any power over their data. But the actual fact, that's overstating it. When you actually say something is schemaless, what you actually mean is that the schema is in your program ambiently instead of in your data, right? You can't look stuff up without knowing where it is. So schema is like, I'm going to encode where it is and give the database some ability to help me. Schemaless is, I'm not going to encode where anything is, and it's on my code to do all the finding of things. So I'm not a fan of schemaless as a formulation. Having said that, what most people think of as schema is, I'm going to make slots. I'm going to make a table and say, okay, in order to be a Twitter account, you have to have these 10 facts, right? Whatever. So we don't want to do that either. So what's the in-between? We're going to have schema that talks only about attributes. We're not going to commit to what entities have what attributes, but we're going to say, there's this attribute out in the world called first name. There's this attribute out in the world called shirt color. There's this attribute out in the world called volume in cubic feet. We're going to have these attributes that things can have, and then they can decide to have them or not as they choose. And the attributes are important because they allow you to make indexes and they allow you to navigate around your system without committing to slots and rectangles. In order to make attributes in Datomic, there are a set of things that you can say about an attribute. You can give it what's called an ident. So anything that has a DB ident, that's giving things names. You can actually give anything you want in a Datomic database a programmatic name. So this is also used for like enums and things like that, where you just want to make up a name and talk about a thing by name instead of by its entity ID. The attribute's going to specify a value type. So this says, is this thing a string or a double or a reference to another entity? It's going to specify a cardinality. Cardinality says, can you have one of these things or can you have many? We already saw that Jane was allowed to like more than one food at a time. The reason that that's true in my data model is that I said the cardinality of liking is many. What would have happened if I said the cardinality of liking is 1, do you suppose? Jane likes broccoli, and then I come back later and say Jane likes pizza. What should we do? I mean, the purpose of schema is to give us some power, right? So what are our choices now? We've said there's a rule in this world that Jane only likes one thing. Or that, actually not Jane, we've said that's important. We've said there's this rule that liking is a thing that only applies to one thing. We don't know who or what kinds of things are going to do the liking yet. We don't care. Liking is going to only happen to one thing. Okay, now what? Well, we have a couple of choices. We could allow the system to move into a state that's inconsistent with the schema. That seems like a bad choice. We could throw an exception, or we could modify the data to make the statement true. And in this case, what this does is we modify the data to make the statement true. So if Jane starts liking pizza after liking broccoli, then Datomic will automatically add a retraction, right? That fifth position in the tuple where we say, is this a fact being added or being removed, will automatically add a retraction saying, you know what? Don't like broccoli anymore. Now we like pizza. You can specify that an attribute is unique. When you say something is unique, you're saying that only one entity in the system can have this attribute. And you can specify that an attribute is a component, which means that it's, the thing is being owned. So an order has a line item, a person has an arm, those kinds of things. And that is going to be a performance hint to Datomic in various places. So I'm going to show you data modeling. You can follow along in this example or look at this example later in code in the Day of Datomic Cloud lab. But I'm just going to walk through modeling a site where people can publish links to things, make comments on those links, and I don't know, maybe upvote or favorite or something like that. So this is, the Hacker News clone data model. So what that looks like in Datomic is, okay, well, the first thing is people are going to they're going to talk about something that happened on the internet. When we talk about something that happened on the internet, we're going to give it a title. So you could just type in a title. That's going to be, we're going to call it a story/title. It's going to be a string. Can things have more than one title? We're going to say no. We're making that choice. A story is going to have a URL. I'm linking to some important announcement that just happened, right? Some famous theorem got proved or maybe didn't get proved, whatever. Story slug, this is not strictly necessary, but we're going to have it here. This is some sort of short thing that we can use when making URLs. So we're going to have some sort of short thing that's not necessarily the title. And then people are going to make comments on it that's a reference because those are other entities, and there can be many of those. The thing about this data model is how close is this to the actual real-world data? It's very close, right? There's no imposition of structure from Datomic when you're doing this. And if you have experience doing modeling in SQL, you may model in more than one step, right? You may do the logical model and then the physical model, or one of them is closer to your domain and the other one's closer to what you have to say to make SQL happy. You don't do nearly as much of that with something like Datomic. What this looks like is a piece of data in Datomic, a map that says my ident is store URL, my value type is string, my cardinality is 1. And you're going to have a little map like that for each different attribute in the system. Likewise, with users on the system, we're going to say users can have a first name and a last name. Those are strings. We're going to say that they have an email. That's unique. That's going to be how they log in. And users can upvote things. And again, most of those things will be cardinality 1, but one of them will be cardinality many. And then comments. Well, comment's going to have a body, which is a string. It's going to have a reference back to who made the comment. So the comment author is going to be an entity, which is a person. And then comments can have comments. And so here you see where Datomic starts to give you some flexibility, modeling hierarchy. What kinds of things can have comments in the system? Well, if we go back, stories can have comments. And now we see comments can have comments. And notice that the attribute name is the same in both places because it's not different. Right? We have identified something in the system that's the same. It's a relationship that can come from more than one entity. Right? It can be a relationship from a story to a comment, or it can be a relationship from a comment to a comment. And I would encourage you to go and model this in SQL to see the kinds of things you get into when you have to model this. So we have news comments as the same kind of attribute. Now, that being said, people tend to think of entities as a group of related things, and I'm demonstrating that relatedness here by having the namespace be common. Right? So I think of comments in the system, they all are prefixed with comment. I think of stories in the system as all being prefixed with story. But that's convention, and that's totally up to you. As a bigger example, you can take a look at the mbrainz sample data set. One of the nice things about this data set is it has a fully worked out schema that was designed by Rich Hickey, who is the designer of Datomic. So this represents modeling the way we would want to do it. The other thing is, it also represents modeling the way we want to do it, which is we draw pictures. So I would never sit down at a keyboard and start typing in maps to model a schema. And so the pictures show you what the different entities are in the system and how they're related. You really can't see this probably at this resolution. But this is relating albums to tracks to musicians, and it's using the open source mbrainz dataset, which you can download and install into the database you created today if you wanted to. So in the next lab, you're going to work through the tutorial where we have some pre-canned sample data that you add. And then when it gets fun, you're going to design data for your own domain. So I'm going to want each of you to pick a domain with which you are familiar and one that you can carve out a very small subset of. So don't fall down the rabbit hole and try to build your entire application, but pick a subset of a domain with which you're familiar and design an object model. But before we do that, I want to take a few minutes to talk about the API that you use to access Datomic, which is really pretty small. I mean, it's a data-driven system, so there's not a lot. There is make a database, connect to a database, transact, and query. And there are a few things around the edges that are going to come up on that, but that's kind of it. But I want to talk about the flavors of it so you understand the pieces and how they work. So the Datomic API is asynchronous at the bottom. It's implemented asynchronously, and it's implemented in this way because, well, gosh, async is super fashionable, right? And also because you can, although with ions you don't have to, you can call Datomic in a traditional client-server way, right? You can have a client over here and a Datomic cluster over there serving requests. When you're doing that, you may often want to have results be paginated, right? When you ask for a query that returns a million things, you may not want to get them all back at once. So the API handles pagination automatically. I think it batches things in units of 10,000 by default. When it batches those things, it puts them on a Clojure core async channel. If you have not used channels before in Clojure, we'll give you a very brief intro to that. But you can think of queues if you've ever used a blocking queue, or you can think of channels in the Go programming language. There are other places that have similar abstractions. And the client API is designed so that when you're using async, it's transducible. So if you're familiar with Clojure's transduce, it's designed to be able to be dropped in there. When you're using async, you never get errors. You never get exceptions thrown. Errors come back as data in the channel. So you get data in the channel that is, here's what you asked for, or you get data in the channel that says, oops, sorry, something went wrong. And then there's a bunch of stuff around dealing with the fact that you're talking to something that's potentially remote. So all of the APIs work the same in terms of being able to specify offsets and limits. I want to go back and get this piece of it, chunking, and specifying timeouts. That being said, for a lot of everyday use, you might be happier to use the synchronous API. The synchronous API is built on top of the async API. It handles all the pagination for you and returns complete result sets, and it will turn errors into exceptions. So if you have something go wrong, it'll throw an exception. So if you're just doing some fairly straightforward thing, that may be more straightforward. And then when you start to run ions and deploy your code into a cluster node, then both of these implementations become local. And so this is the same API, but it's actually happening in memory and not going across the wire anywhere. So the sync API tends to be a function like pull with two arguments, either a connection or a database. So connection is I want to transact, or a database is I'm working against a point-in-time value, and then some sort of descriptor in data of what you want. This is saying, go and find the entity ID whose name is Jane, and then tell me, select everything about it. And we'll see more of pull later, but this is a very powerful thing because it allows you, if you open up your API to do this, if you let people send in pull specifications, you don't have to decide in advance what kind of information about an entity you want to return. And callers can then say, I'm interested in shaving off this piece, I'm interested in shaving off that piece. This is a quite complex example of the async API. It's demonstrating at the top, specifying all the common args explicitly. So start at the 10th one of these. I'm willing to wait up to 60 seconds. I want them 1,000 at a time, and I only want the first 10,000 of them. And then it's showing doing a Clojure transducer over these. And so what this is doing is it's saying, I want to do a reducing operation that says I am pulling out the frequencies. So I'm grabbing all, and the datoms is a raw API. So this is a low-level API. This is not query or pull. But this is saying, grab every datum in the entire database. So this is not a very speedy operation, necessarily, if you had a big database. And then that map frequencies of A is saying it's calling frequencies on it a chunk at the time. So it gets back a chunk of 1,000 things, and it gets a frequency table that says there was this many of this attribute, and this many of that attribute, and this many of that attribute. And then it rolls them up by merging them. So every sub-frequency table is being merged, adding together the results. So we get back an aggregate frequency table. And this will slurp the entire database through and do some MapReduce kind of operation like we're doing here without ever having much of the database in memory at a time, necessarily. So if you did this on a really big database, it would take a while, but you wouldn't have to pull the entire database into memory at once. Yes? Can transduce work in parallel? Yeah, so there's not a parallelism baked in at this level. There is parallelism baked in other places. So the more common case where parallelism comes into play is query executes in parallel. If it decides that you've got clauses that it can go off and do simultaneously, it will spawn threads and do that for you. But no, using it like this is not parallel. Was there another question? There was a half question that went away. All right, So there's one more thing I want to talk to you about because you'll encounter it because it's a lab setting and we're going to make mistakes, and that is how to understand what happens when things go wrong in Datomic. And as everybody knows, the key to understanding problems is Hall & Oates. So it turns out that Hall & Oates, over the course of their careers, released a set of songs that encoded all of the things that can go wrong in programs. And so the library that Datomic clients use to report errors is directly inspired by Hall & Oates. We've translated the names from the songs into more programming names. We had to avoid copyright infringement. But I'll show you the table that will let you understand what can go wrong. So if you try to talk to a server and it's not there, you're going to get unavailable, or as Hall & Oates would say, out of touch. If you set a timeout such that you can be interrupted, such that you can be told that this job was interrupted because we gave up, then you can get back an error that says, I was interrupted. It doesn't matter anymore. If you keep trying to submit queries that are broken, you never learn, but you're going to get back an error that says, that's incorrect. If you try to do something that's illegal from a security perspective, I can't go for that. That's forbidden. If you dream that something can be done, but it can't, you're imagining that, but that's unsupported. If a resource is not found, well, it's gone, sorry. If you encounter a conflict, if you try something that conflicts with the state of the system, you should give that up. That's not going to ever work. It's not going to work now. It's not going to work tomorrow. And if the server blows up, that's a fault. Or if something happens that we don't understand, something went wrong that we don't know, then you're just falling down. That's a fault. And then finally, if you should retry this in a minute because the server's busy, then you'll get the busy/wait for me error. All of these show up as keywords in a closure map. So if you're using the async API, you'll get a piece of data that has an anomalies category of one of these things. If you are using the synchronous API, you'll get an exception from closure that has data in it. It's worth talking about why we did this, because it would be easy to assume, hey, we're in closure instead of Java, and we're using Datomic instead of SQL, and we did Datalog instead of the relational algebra, that we have some sort of huge not invented here syndrome going on the Datomic team. And that is not true at all. We have worked heroically to try to use existing tech, which is why Clojure runs on Java. It's why Datomic embraces AWS. Wherever tech can possibly do what we're trying to do. But the other opportunities in this area don't quite work. The HTTP status codes are not terrible. They actually represent an attempt at this. We're going to partition things that can go wrong, and it's either a this or a that or a that. The problem with HTTP status codes is they don't actually cover the cases that go wrong when you didn't actually talk to anybody. Right? Some of the failures mean I couldn't get there. There can't possibly be a status code returned from the server that means nothing was returned from the server. So they can't cover the space that way. Also, HTTP status codes are, like everything in the HTTP protocol, evolved over time and are complected with other things and have status codes like I'm a teapot that probably you really shouldn't. That really is an HTTP status code, I'm a teapot. So there's all these status codes that don't sort of make sense. On the other hand, exceptions, Java style, sort of try to do this, but that's also kind of broken. And it's broken because they didn't have, the objective here is to have a fixed set that partitions the world that you could, at least some of the time, beneficially branch on when you had a problem. If the set's not fixed, you can't really branch on the things you don't know. So it is fixed. It's not like Java exceptions that are wide open. And we have found this to be helpful because you can actually write programs that say, well, when these 3 kinds of things happen, I'm going to go over here. When those 4 kinds of things happen, I'm going to go over there. So that's what's going on there. Okay. So for the next lab, there's the follow-along portion, and then there's the be inventive portion. The first portion, work through the assertion tutorial and the read tutorial to get a little bit more familiar with the Datomic API and putting data in. And you should be able to click on those links, and those should go to the tutorials. Then the second part is make your own schema. So pick a very small domain. I would say if you're doing more than 15 or 20 attributes or more than 3 or 4 different entities, way too big. And then describe that in the most concise, effective way you can. Draw a tiny diagram showing how the pieces fit together. And then write a schema for that in Eden and transact it into a database. And of course, if you finish all that and you have time, rock on, start making some data, right, in your sample world. So it is 11:30 now. I am going to give you the benefit of getting to lunch early because I'm going to announce lunch. I'm going to try to announce lunch a few minutes before the other rooms announce lunch so that you can get out there first. So we're going to take a break to work on this lab, and then inside the lab break, there will be the lunch break. So in like 20 minutes, I'll say, okay, everybody, let's all quietly sneak out of the room and get to the food before everybody else gets there. So any questions before we start on the lab? Yes?
You posted an image instead of slides.
It only dropped an image? Yeah. All right, well, I will post the slides again because that's not going to work. Also, if you're following along in the tutorial on the Datomic docs site, these are the next two things in the site as well. So you can, I will also just post the links directly into Slack when we're done here. Thank you for pointing that out. Any other questions? All right, let's go make schema.